Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 3. Applications of the derivative. Section 4.3. How derivatives affect the shape of a graph.
Lesson 3. Concavity and Inflection Points. Part 1. Okay, so the next thing we're going to look at is the idea of concavity, which is the way that a curve is curving or curling. So if you think about a function that is increasing, here I have a function that's increasing, here I have a function that's increasing. Ignore these pictures at the bottom for a moment. Notice that this is increasing, but it's scooped upwards, it's sort of curled upwards. And this one is increasing, but it is scooped downwards, it is curled downwards. When something is scooped upwards, we say that it is concave up. And when something is scooped downwards like this, we say it is concave down. Now, we could also look at a curve that is decreasing, and a curve could decrease and be concave up, or decrease and be concave down. So if you look at these bottom two pictures, this is a decreasing function, this is a decreasing function. This one is decreasing but scooped upwards, so it is concave up. This one is decreasing, but it is scooped downwards, so it is concave down. Sometimes people like to think of something that is concave up, whether it's increasing or decreasing. This is partly decreasing and partly increasing. Concave up, they like to think, oh, that's like a cutaway of a cereal bowl or something like that. And if you poured water into a curve that is concave up, it would hold water. But if you thought about something that is concave down, and here it's partly increasing, partly decreasing, but it is scooped downwards, that would be concave down. We sometimes abbreviate it con down. And you notice that if you poured water into this one, the concave up, you were pouring water in here, it would be like a bowl and it would hold the water. But if it's something that's a bowl that's turned upside down, the water would just splash off of it, so doesn't hold water. It would be something that's concave down. Okay, well, we want to know in terms of the derivatives of a function what tells us when a curve is concave up, when it's scooped upwards, and when it is concave down, scooped downwards. And in order to understand that, I want us to go back and recall the following fact. We said a function is increasing only if its derivative is, and let's see if we can remember, so if you think of f is increasing, we said it's increasing if its derivative is positive. Remember, a function is decreasing only if its derivative is negative. So a function is increasing if its derivative is positive. All right, so keep that in mind. So now I want you to think about a curve f whose graph is concave up. So it's something that is scooped upwards. And I've picked out 3 points along that curve, but you could think of any point along this curve. And let's try to think about the slopes of the tangent lines to that curve at those 3 points. So the tangent line here looks maybe something like this. I can get my pen to write. And then here it looks like the tangent line might be something like this. Better use a different pen. So here the tangent line looks like this, here the tangent line looks like this, and here the tangent line looks like this. And what do you notice about these 3 tangent lines? Because the curve is scooped upwards, it looks like the tangent lines are getting steeper and steeper. Well, what does that mean about the slopes of those tangent lines? If I look at the slope of this tangent line, it looks like a fairly small slope. I might go over 2 units for every unit that I rise. So I'd have a rise of 1 and a run of 2. If I look at this next tangent line, it looks like the slope is larger because it's a steeper line. Maybe the slope is 1. You could think of it as a rise of 1 for every 1 unit we move to the right. And if I look at the slope of this last tangent line, it looks even steeper. Maybe it's a slope of 2. You can think of that as 2 over 1. I'm going up 2 units for every unit that I move to the right. So what I want you to notice is that these numbers for our tangent lines, as we move to the right on the x-axis, the numbers for the tangent line are getting larger. You have a half, and then 1, and then 2, and if you continued this, maybe you'd get to a tangent line slope of 3, and so on. So the slopes of the tangent lines, as we move in the positive x direction, the slopes of the tangent lines is increasing on this concave up graph. But don't forget that the slope of the tangent line is just another way of saying the derivative. F prime of x is the slope of the tangent line at the point x. So if we say the slopes of the tangent lines are increasing, that means f prime is an increasing function. Okay. But what did we say up here? We said a function is increasing only if its derivative is positive. So f prime can be increasing only if its derivative is positive. All right. But let's think about f prime. It's a function in its own right, so it has a derivative. What's the derivative of f prime of x? Its derivative is f double prime of x, the second derivative of the original function. So all of this stuff will happen only if f double prime is positive. Let's run through it in this direction once more, and then we're kind of going to go backwards. So we have a function whose graph is concave up. We notice that the numbers for the slopes of the tangent lines are increasing. But we said, hey, the slope of the tangent line is just the derivative, f prime. So f prime is an increasing function. But any function, including f prime, can only be increasing if its derivative is positive. So f prime is an increasing function only if its derivative is positive, but its derivative is f double prime. Now we're going to follow this logic backwards. If f double prime is positive, that would mean that f prime is an increasing function, which means the slopes of the tangent lines are increasing, and that would go along with tangent lines that are getting steeper and steeper, and the only kind of curve that can work for that is a curve that is concave up. Let's jump down to here then and try to write this first statement in this theorem, and then we'll come back and consider something that's concave down. So what we just said, if you follow these bubbles backwards, is that if f double prime is positive, that is, if f double prime is greater than 0 on some interval of x values from a to b, that means, and I'm just going to kind of put the in-between bubble in here, although it's not part of the statement of our theorem, that means that f prime is an increasing function because its derivative is positive. That means that the slopes of the tangent lines are increasing, so you have steeper and steeper tangent lines, and the only kind of curve that can go through that is a curve f that is concave up, scooped upwards. And you can see the only kind of curve that would have steeper and steeper tangent lines would be one that is scooped upwards, concave up. Okay, let's go ahead and think about f being concave down, and we can use the same kind of argument. So here I have a function whose graph is scooped downwards, and I picked out 3 points on the graph, although there are lots of points that you could choose. You could choose any points that you want to, but let's go ahead and think about what happens to the tangent lines to this graph as we move to the right in the positive x direction. Well, I can see that these tangent lines are getting shallower and shallower. So maybe the slope of this first tangent line might be equal to 1. The slope of this second tangent line, maybe you go up 1 unit and over 2 units, so its slope might be 1/2. And this third tangent line is pretty close to horizontal, so it's going to have a small value. If I go up 1 unit, it looks like I might go 3 units to the right. So maybe it has a slope of 1/3. Think about these numbers for the slopes of the tangent lines. 1, 1/2, and then 1/3. Well, those numbers are getting smaller. They are decreasing. So what can we say? The slopes of the tangent lines, as we move to the right on the x-axis, these slopes are decreasing. So the slope of the tangent line is decreasing. But again, what is the slope of the tangent line? Well, that's just the derivative of my function. So slope of the tangent line, same thing as f prime of x, so f prime of x must be a decreasing function. But a function is, well, we did, a function is increasing. A function, if I change this to decreasing, a function is decreasing only if its derivative is negative. So f prime will be a decreasing function only if its derivative is negative. Remember, when a function has a negative derivative, it means it's a decreasing function. So f prime is decreasing only if its derivative is negative. But what is the derivative of the derivative? What's the derivative of f prime? It's f double prime of x. So f prime is decreasing only if its derivative, namely f double prime, is negative. Now let's follow this logic backwards. If f double prime is negative, that means f prime must be a decreasing function, which is the same thing as saying that the slopes of tangent lines are decreasing. But if the slopes of my tangent lines are decreasing, it means the tangent lines are getting shallower and shallower, and the only kind of curve that could go with that is one that is concave down. So let's go ahead and state that formally in our theorem. If f double prime is less than 0 on some interval of x values from a to b, so if f double prime is less than 0, same thing as saying is negative. Well, what does that mean? I'm going to put the little in-between bubble in here. That means f prime is decreasing as we move to the right. That's what's in here. But for something to have derivatives that are decreasing, slopes of tangent lines are then decreasing, so that means my tangent lines must be shallowing out, getting closer and closer to horizontal, because their slopes are decreasing, smaller and smaller slopes, and the only kind of curve that could go with shallower and shallower tangent lines is a function that is concave down. So the first derivative, f prime, told us, the sign of the first derivative told us whether the function was going up or going down, whether it was increasing or decreasing. And what we've just found out is that f double prime of x tells us something about the graph of f as well. It's a little bit more subtle behavior of the graph. It's sort of the way that it's going up or the way that it's going down, the way that it curls as it goes up or down. But when the second derivative is positive, the curve is concave up. When the second derivative is negative, the curve is concave down. So the second derivative is going to tell us about the concavity of our function. I should really say the sign of the second derivative tells us about the concavity. Sign of the first derivative tells us about whether the function is increasing or decreasing. Sign of the second derivative tells us about whether it is concave up or concave down. Now what I'd like us to do is to go back to our 3 examples and analyze each of those for their concavity. So let's return to example 1. So we're kind of flipping back again to this example 1. It is on the 3rd page of our handout. We've already done parts A and B where we decided where the function is decreasing and increasing, and we located sort of the important points between, the transition points between increasing and decreasing, or vice versa, which were called the local maxima and minima of the function. Now what I want us to do is part C and D, and we'll also try to draw a fairly nice graph of our function. In part C, we're asked to analyze where is the curve concave up and where is the curve concave down. All right, so how do we do that? We just got through saying that the sign of f double prime is going to tell us where the curve is concave up and where it's concave down. So we need to find f double prime. So our first step in answering this question will be to find f double prime of x. Well, we've got f prime of x up here, and we have it in factored form, but it's easier to find the second derivative from this state where we have separate terms. So I'm going all the way back up to here. F of x was this function, 3x to the fourth minus 4x cubed plus 1. We took the first derivative, that gave us 12x cubed minus 12x squared, and now I want us to find the second derivative. So I'm taking the derivative of f prime. It looks like that would be 36x squared minus 24x. Okay, good. Well, that's not in a very good form for determining when that expression is positive and when it's negative. So let's factor it just the way that we did with the first derivative. So let's see, I could pull out, I guess, a common factor of 12x. Let's see what we're left with inside. It looks like I would have a 3x minus 2 inside. So that is my second derivative. And I want to know where this expression could be changing in sign. Well, it could be changing sign when this factor is 0, 12x is 0 when x equals 0, or when this other factor is 0, 3x minus 2, and if it's hard for you to do in your head, just take that factor and set it equal to 0. 3x would be equal to 2, and so x would be 2/3. So x equal 2/3 is the other value where f double prime might be changing sign. Well, as I said, these numbers where the second derivative could be changing sign don't have a term associated with them like critical numbers. So I just give them my own terminology. I call them special numbers of f. But there isn't really a formal term, but just to distinguish it from critical numbers, which are really places where the first derivative could be changing sign, these are numbers where the second derivative could be changing sign. And how do we determine, those are the places where it might be changing sign, how do we determine what those signs are? We do it exactly the way that we did for the first derivative. So mechanically, this process down here is exactly the same as what we did in part A, except that instead of analyzing the sign of f prime, we'll be analyzing the sign of f double prime. So I take my special numbers and I put them on the number line. And I usually like to draw them so that this number line is right underneath this number line, so you notice I've tried to kind of line up the zeros here. And let's see, 2/3, that's going to be a little bit to the left of 1, so 2/3, that fraction would be right about here. And those are my special numbers. And now what I want to do is to analyze the sign of f double prime of x in each of the intervals that I end up with. These are the only places where the sign could be changing sign, so the sign has to be like all positive or all negative in this interval to the right of 2/3, and similarly for the interval between 0 and 2/3, and for all x's to the left of 2/3. And that means that in order to analyze this, I can go ahead and just use test numbers exactly the way that I did for analyzing the sign of the first derivative. So I'm going to put some test numbers in here. I just pick anything that I want to the right of 2/3. You could pick 1 if you want to. So here's my test number. And I think about plugging 1 into this expression here for f double prime. Maybe I'll put a little green box around this so that we can see it. If I plug 1 into this, it looks like the first factor, 12 times 1, would be positive. The second factor is also positive. 3 times 1 is 3, minus 2 is 1. That's positive. Positive times positive gives me an overall positive sign for the second derivative. So it must be positive for all x values to the right of 2/3. What about between 0 and 2/3? You can pick any number you want to, maybe pick 1/3. So I think about putting the number 1/3 into here. This factor will be positive, 12 times 1/3. 3 times a third is 1, minus 2 is negative 1, so it looks like this factor is negative. So I have a positive factor times a negative factor. That's going to give me a negative answer. So my second derivative is negative in here, and I'm sorry my pen is sort of melting here. I don't know why. Lights are too hot. Okay. Now let's try choosing a test number that is to the left of 0. You could choose something like -1. And we plug -1 into the first factor. That makes the first factor negative. If I plug -1 into the second factor, that'd be -3 minus 2. That's -5. That's also negative. Negative times negative will give me an overall positive sign. So unlike the first derivative, which stayed the same sign on both sides of 0, the second derivative actually switches sign. Okay, well that's great, but what does that mean about my function? Let's see if we can decide. We know the signs of f double prime. That means something about the graph of the original function f. Okay, remember we're now looking at the second derivative, and if the second derivative is positive, as it is for the values to the right of 2/3, remember the second derivative tells me not whether the function is going up or down, but whether it is concave up or concave down. And if the second derivative is positive, the curve is concave up. And schematically, the curve may not look like this, but schematically we just draw a little kind of bowl shape that's upwards. So that reminds me that it's concave up, or you can write the words concave up in there if you want to. But for me it's easier to sort of see a picture. It's scooped upwards. Okay, between 0 and 2/3 we said the second derivative is negative, and remember that means that the curve is concave down. So schematically that's not really exactly what the curve will look like, but we're just saying it's going to be scooped downwards. And to the left of x equals 0, the second derivative is positive again, and so it's going to be scooped upwards. Okay. Well, there are going to be these points that are transitions. You notice right at x equals 0, we're going to have a transition from concave up to concave down. And at x equals 2/3, there's another transition. In this case, from concave down, going to a curve that is concave up. Those transition points are what are referred to as inflection points. That's what it's talking about in part D down here. Unlike max and min, which sort of distinguish between whether you're going from decreasing to increasing, that would be a local minimum, or increasing to decreasing, that would be a local maximum. We don't distinguish with inflection points. If it's going from concave up to down or concave down to up, it's just called an inflection point. And you notice that's what's happening if I look at just x equals 0. My curve is going to be switching from being scooped upwards to being scooped downwards right at x equals 0. So as long as my original function is defined at 0, it will be because it's a polynomial and it's defined everywhere, I will have an inflection point at 0, comma, whatever the corresponding y-coordinate is. So there'll be an inflection point right here at x equals 0. Well, how do I find the corresponding y value for x equals 0? Remember, we're looking for a point on the graph of our original function f, because after all, that's what we're going to try to do eventually, is to graph f of x. So I want a point on the graph of f, my original function. So to find the corresponding y value, I'm going to be plugging into the original function. So my inflection point will be at 0, comma f of 0, and let's see if we can figure out what that is. If I plug 0 into my original function, actually we did it down here, I get 0 minus 0 plus 1, I get 1 for the corresponding y-coordinate on the graph of the original function. Okay, let's look at x equal 2/3. If I concentrate on that part of it and cover the rest of this up, you notice to the right of 2/3 the curve is concave up, to the left of 2/3 it is concave down, so it is switching concavity at this point, and that means I will have an inflection point there. I should write inflection point, sometimes we abbreviate it this way, at 0, 1, and now I'm going to have another inflection point at this other special number 2/3, because the concavity is switching from one concavity to another. So at 2/3, and how do I find the corresponding y-coordinate? I have to plug back into the original f, so at 2/3 comma f of 2/3, I will have another inflection point, another place where the concavity is changing or switching. So let's see what point that is. If I plug 2/3 into the original function, it's a little tricky because you got a fraction that you're plugging in. So I'm going to cheat and look at my notes, but I just plugged 2/3 in. I did 3 times 2/3 to the 4th minus 4 times 2/3 cubed plus 1. And I simplified that whole thing and I got 13/27. So let me write that over here a little bit bigger so you can actually see it. 2/3 comma and f of 2/3 is 13/27. And I think I even threw that into a calculator for graphing purposes. This point is approximately, what did I get? It's about 0.6. It's really 0.67 because it's 2/3. And the other value is about 0.5, at least to the nearest tenths. So that's that point. For graphing purposes, it's nice to plug into a calculator. Okay. Oh, and to answer this question more formally, the way that we did up here in part C, where is it concave up and where is it concave down, let's go ahead and do that. I didn't do that. Let's just write formally f is concave up, and let's list the intervals on which it is concave up, and we'll try to list the intervals on which it is concave down. So let's see if we can do that before we leave this page. Well, where is it concave up? It's concave up whenever x is less than 0 or greater than 2/3. So it's going to be concave up from -infinity all the way up to 0. And here I will put a square bracket. And then I'm going to say or you can put union if you want to, or whenever x is from 2/3 up to positive infinity. So from 2/3 up to positive infinity. And where is it concave down? It's concave down between 0 and 2/3, so it's concave down from 0 to 2/3. And again, whether you put a square bracket and include the endpoint or a rounded parentheses at these special numbers probably is kind of a picky point that your instructor won't care about. But technically, because of the way that concavity is defined, the most perfect answer is to actually include the endpoints. Okay, let's go ahead and see how this affects the graph of our function. So remember that what we did, and I'm going to put our old overhead right here. On the next page, we started to graph this function, and we used the information from A and B, and we wrote down, oh, the function's going down till it hits the local minimum, and then it is going up from then on. There were no other local max or min. So this was, we called it the overall kind of crude behavior of the graph. Now what I'm going to do is to add in the concavity. So let's see if we can add this information. We have an inflection point at 0, 1, which is this point right here on the graph. And there's another inflection point at 2/3, 13/27. So 2/3, I said, is about 0.67. It's 2/3 of a unit here. And then I go up 13/27, which is just a little bit less than a half. So it's a point that's maybe right about here. So I have another inflection point at 2/3 and 13/27. And this inflection point was at 0, 1. Okay, now if we look back at our chart, I'm going to put that up here just for a moment in case it's hard to see over there on the left. We said that it's going to be concave up until I get to that inflection point at 0. So I'm going to think of doing my graph sort of from the left to the right. And it's going to be concave up till I get to my first inflection point, and then the concavity will switch to concave down. So let's concentrate on that first inflection point right here, and I'm going to think of drawing my graph coming in from negative infinity. Now keep in mind that whatever our concavity is that we add to this graph, we still have to follow the overall behavior of where it's going down and where it's going up. That's expressed by this dotted line here. So I have to be going down until I get to this inflection point, but I have to be going down in a way that the curve is concave up. So for this whole interval from minus infinity up to 0, we said that the curve is going to be concave up. So I'm going to have a decreasing curve, but it won't be decreasing and scooped downwards, it will be decreasing and scooped upwards. So I have to make it go down and yet be scooped upwards. And I'm going to exaggerate the concavity just a little bit so that you can see it. The curve, we'll put in a few more points later and make it more accurate, but just so you can see the concavity. Notice the curve is falling, it's decreasing, but it is scooped upwards. Sometimes it's a little tricky for people to get at first, so it takes some practice, so be patient with yourself. Okay, we said once we get past this inflection point, the concavity switches. So in this little region from 0 up to the next inflection point, which is at 2/3, the curve switches and becomes concave down. Notice that's what we said on our chart. I'm going to put the chart back for a moment. We said between 0 and 2/3, the curve has a negative second derivative, and so it is scooped downwards. So keep in mind, I must still make my curve be decreasing because I have to follow this green dotted line. So the curve has to be going down. But from this inflection point to the next inflection point, the concavity switches. It is no longer scooped upwards, it is now scooped downwards. So I have to be going down, but I have to be going down in a way that is curled or scooped downwards. So it would have to look something like this between the first inflection point and the second. So decreasing and concave up to the first inflection point, then decreasing and concave down to the second inflection point. Okay, what happens after that? Well, from here onwards, from 2/3 onwards to positive infinity, remember the function switches to concave up again. It's an inflection point. It's going to be a place where the curve is switching concavity. That's what we said on our chart. If you look at the point corresponding to 2/3, the curve is scooped downwards, and then it switches and becomes scooped upwards. So I'm going to look at my green dotted line here. Notice it's going down for part of this time, and it's going up for part of this time. But whether it's falling or rising, I have to draw something that is scooped upwards. I can't continue to draw something that is scooped downwards because the concavity from this inflection point on is the concavity is upwards. The second derivative is positive. So I'm going to keep following this dotted line, meaning that I have to have something that's going down, but I'm going to switch back and make my curve scooped upwards. So it's scooped downwards up to this point, and then it is scooped upwards. And again, I'm kind of exaggerating the concavity just so that you can see it on this tiny graph. When I get past the local minimum, notice the curve is now rising. I have to follow the green dotted line, but it's going to be rising and scooped upwards. Okay, let's step back for a moment and just notice, kind of double check, yes, I've drawn a purple graph that is going down where it's supposed to. It's supposed to go down till I get to my local min, so that follows the overall rough behavior of the dotted green path. And then it is rising after that, so I am following the dotted path in terms of overall down and then up, decreasing and then increasing. But I've added in this subtle behavior of the concavity. It is going down and scooped upwards till we get to the first inflection point. Then between that inflection point and the next, it is going down but scooped downwards. And from that inflection point on, it is going to be scooped upwards. So it's going to go down, scooped upwards, and then it is increasing and scooped upwards. And there won't be any other changes in the concavity. So I don't want to kind of be sloppy and sort of make it bend like this, because that would be switching back to concave down. I want to draw my graph in a way that it's clear that this curve stays scooped upwards. It doesn't, I don't want to get sloppy and, you know, maybe make it look like this, because that would be another inflection point where it switches from scooped upwards to scooped downwards. So you don't want that. So this is actually a pretty good graph of my function. How many points though have I actually plotted? I have only plotted 3 points, 1, 2, 3. And back in algebra, if you were asked to plot the graph of a polynomial of 4th degree, you'd have to do a lot of points before you could get a graph that was this accurate, and you might never know exactly where the local min is or where these inflection points are. So this turns out to be a pretty accurate graph, but it only has 3 points plotted on it. So at the end, we usually try to do a few extra points, and I usually say that we try to do well-chosen extra points. And students always ask me, what do you mean by well chosen? Usually what we mean are, we're going to choose some x values that we don't already have points for, that are close to interesting things that are happening on our graph. For example, that are close to the inflection points or close to the max or min on the graph. So what might you choose as a point? And of course it might be slightly different values for each person, but what might you choose? I don't know, I might choose something like -1. That's kind of close to this x value of 0 that goes along with this inflection point. So I might choose -1. I might choose 2, that would be on the right side of this local min, and you might choose a few other points. If you want it to be even more accurate, you could choose something, say, between -1 and 0. I think I chose -0.5, because that's kind of adding in more points on this side. And I think I put in 1.5, which is 3/2. So I think I also did 3/2. You might choose slightly different values to plug in, and that's fine, but you want to choose values that are close to the interesting things that are happening and give you a more accurate graph. And also, it's hard for me to know kind of how steep this graph is. I've drawn something that's increasing and concave up, but is it really steep like this, or is it really shallow like this? So that's why I like to get points that are sort of outside of the interesting points. So that's why I chose the -1 and the 2. Well, to find the corresponding y values, remember you always plug into the original function, because we're trying to graph the original function. And I did that. I'm going to cheat and look at my notes. When I plugged -1 into the original function, I got 8 as an output, which is actually, I think, off of my graph. That might be why I chose -0.5. So when you plug in -1, you're up at 8. So that's actually off of my graph up here somewhere. So I haven't drawn something that's quite steep enough. And when I plugged in 2, I got 17. Well, unfortunately, 17 is also off of my graph. So you can see that my graph is not sort of narrow enough, it's not steep enough at the edges. This is going to go shooting up here much more quickly than what I have. Well, since these are off of my graph, that's actually why I chose them, to show you that, okay, if that's off of the graph, then that's why I chose -1/2, something that's a little bit closer in. When I chose -1/2, I got 27/16, which is approximately 1.7. So yay, that's something on my graph. So at -1/2, I'm supposed to be all the way up at 1.7. So what I drew really isn't quite right. It should be the same shape, but it should be going up rather more quickly than what I drew. And so I would cross that out, and you just want to draw it in a way that it's clear that that's still concave upwards everywhere to the left of this inflection point. I plugged in 3/2 and I ended up getting 43/16, which is approximately 2.7. So when we plug in 1.5, 3/2, we're up at 2.7. And you can see again that my graph is really not quite accurate, it should be going up much more steeply than what I've shown. So it should be looking more like this. And I'll cross this out. Well, that's all kind of messy. So usually we'll draw a final graph down on the bottom, or some people will draw all of these things very lightly in pencil, like a green pencil maybe for the overall dotted green path, and then a light colored pencil for fitting in the concavity. And then when you add the extra points, you get something that's really quite a bit more accurate. And so then they'll draw that graph in a heavy pen or something, so it's clear that that's the final graph and that's their final answer. But let me just try to draw this a little more accurately for you. So this was our inflection point at 0, 1, and then there was another inflection point at 2/3 and a little bit less than a half, so there was an inflection point here, and then there was a minimum at 1, 0. And the other points that we had were the -1/2 and 1.7, and the 3/2 and about 2.7. And so I'll just try to draw what I have up there. Be sure that this looks like it continues to be scooped upwards and you don't bend it over and make it scooped downwards. Between these two, it is something that will be scooped downwards, and then it switches to scooped upwards, and then you have to try to draw something that's very steep but scooped upwards, and it's a little tricky, but you'll get used to, you'll get better and better at drawing these graphs. So this would be my graph of the original function f of x is equal to 3x to the 4th minus 4x cubed plus 1. It's always nice to label your final graph. Okay, well, let's go ahead and we'll look at example 2. So moving to the next page, this is page 5 of the overall section. Remember that we actually already did part A, where we found where the function was going down and where the function was going up. And we found, in this case, there was one local minimum that occurred at 1, 0, sometimes called a relative minimum. Same thing. Let's look back at the graph that we did on the following page. That's page 6 of our handout. And just to remind you that so far all we've done was put the information from parts A and B down here. Here's our dotted green path that shows the rough behavior of the curve. It's going down until I hit this local min at 1, 0, and then it is going up from then onwards. Well, let's try to figure out more detailed information about our graph. In particular, we're going to now look at the concavity. How is the graph going downwards? How is it going upwards? Is it scooped upwards? Is it scooped downwards? And if so, where? So that has to do with parts C and D. Where is the curve concave up and where is it concave down? And we already saw in example 1 that that has to do with the sign of f double prime of x. When this is positive, the curve is scooped upwards. When this is negative, the curve is scooped downwards. So we have to find the second derivative. Well, let's rewrite down the first derivative. And we have the first derivative in simplified form here. That was a nice form for determining where f prime was positive and where it was negative, finding the critical numbers. But let's go back up to this stage to find the derivative of f prime. I think it would be easier. So I'm just going to write it this way, 2/3 x minus 1 to the -1/3. So that's f prime, and that's what we want to take the derivative of to find f double prime. Well, to find f double prime, let's see what rule I have to use. I really have an inner function, namely x minus 1, inside the x to the -1/3 function. So since I have a composition of two functions, I will need the chain rule here, just as we needed the chain rule for the first derivative. So the 2/3 is a constant multiple. That's just going to get carried along. But to take the derivative of x minus 1 to the -1/3, I need the chain rule, so I'm going to take the derivative of the outer. That means I pull down the negative 1/3. It's going to be whatever I evaluate this derivative at, to one lower power. Let's see, negative 1 minus 1. That's negative 1 minus 3/3. That'll be negative 4/3. And where do I evaluate that? I have to evaluate it at my inner function. So this is derivative of the outer. I'm evaluating it at the inner, which is x minus 1. And by the chain rule, I have to multiply that by derivative of the inner. But derivative of x minus 1 is just 1, so that doesn't change anything. So that is my second derivative. Let me clean it up a little bit. F double prime of x would be, let's see, these would multiply to negative 2/9, x minus 1 to the negative 4/3, excuse me. But to decide where this is positive and negative, it is nicer not to have negative exponents in our expression. So I'm going to make that exponent positive by moving that factor into the denominator. So we would end up with negative 2 in the top, I have a 9 in the bottom, and I'm pushing the x minus 1 to the 4/3 in the bottom. So the exponent changes to positive. And let's just rewrite that in root form instead of fractional exponent form. So I'm going to write it this way. Let me just rewrite f double prime of x is equal to negative 2 in the top over 9 times the 4/3 power is the same as taking the cube root of x minus 1 raised to the 4th power. Remember, the number in the numerator of our fractional exponent tells you what power to raise your base to, and the number in the denominator always tells you what root to take. Okay, that's my second derivative. I want to determine all the values of x where this expression might be changing sign. So those are going to be values where either factors in the numerator or the denominator of this fractional expression are equal to 0. Well, the top is a constant. It's always negative 2. So there's no value of x that's going to make the numerator of that expression 0. The 9 is a constant factor. But this factor, x minus 1, could be made 0 by letting x equal 1. So that's a value where x minus 1 to the 4th, cube root of all that, might be changing sign, and therefore the overall expression might be changing sign. Remember that for the first derivative, such numbers where the expression could be changing sign are called critical numbers. For the second derivative, we call those special numbers. Which is not an official term, but it's my term, just to distinguish it from critical numbers. So x equal 1 is our special number. Interestingly, it also happened to be a critical number for our function. It corresponded to a minimum. So we just put it on there, that's okay. So x equal 1 is both a critical number and a special number, that's fine. And now what we want to do is to try to check the sign of f double prime of x to the right or the left of its special number. This special number divides the number line into 2 intervals, and whatever the sign of f double prime is, it has to be the same for all x's to the right of 1, and it has to be the same sign for all x's that we would plug in to the left of 1. Well, that means we get to put in test numbers. So let's go ahead and do some test numbers, just as we did for the first derivative. And I just pick any value that I want to that's definitely bigger than 1. Say I choose 2 as a test number. I throw that into f double prime. F double prime of 2 would be negative 2 over 9 times, well, when I plug 2 into this factor, I have 2 minus 1, that's positive. I raise it to the 4th power, that's positive. Take the cube root of a positive number, you get a positive number. So this is going to be positive when I plug 2 into this expression. The top of the expression is negative. I have a positive 9 times another positive factor. So I have an overall negative over positive times positive. It looks like the overall sign of that fraction is going to be negative. So the overall sign of f double prime will be negative. That's true at 2, and so it's true for all values in this interval x greater than 1. Okay, how about a test number that is to the left of 1? I was going to choose 0, I'm thinking ahead. To the left of 1 I might choose 0, that'd probably be the easiest, but you can choose any number to the left of 1. And if I choose 0 and I plug that into here, you notice that when I replace x with 0, I get 0 minus 1. That's negative 1. So that is going to be something that is negative. But what happens when I raise that to the 4th power? That is going to become positive. And if I take the cube root of a positive value, this will be positive. So negative 1 to the 4th is a positive 1. Cube root of positive 1 is positive 1. And so I would again end up in a situation where I have a negative over a positive times another positive. And that's because we were raising this factor to an even power. So the sign of f double prime actually does not change on the other side of its special value. It stays negative. In other words, f double prime is negative for all x values except right at 1 where it's actually undefined. Well, what does that mean about the graph of my function? It means that if I look to the left of 1, I will have something that has a negative second derivative. That means that my curve is concave down. And remember, schematically, we just draw a little upside down U for concave down. When I look to the right of 1, my second derivative is still negative. So what does that mean? It means my curve stays concave down. So this is not a curve whose concavity is switching anywhere. It's concave down to the left of this special number. It continues to be concave down to the right. What about inflection points? Would this point corresponding to x equal 1 be an inflection point? Well, remember we said that an inflection point is a place where the concavity is switching. Concavity must switch. And is this a place where the concavity is switching? It is not. It's concave down. It stays concave down as we go to the right of 1. So concave down to the left, concave down to the right. The concavity does not switch. So what does that mean? It means that in this case, we have no inflection points. Unlike our last example where we had 2 inflection points. So we have no inflection points, and I guess I could also write down formally an answer to part C the way that we wrote a formal answer to part A up here, where is the function increasing, decreasing. Let's write down formally that f is concave down. Well, it's really concave down from minus infinity to 1, and then again from 1 to positive infinity. And because we can either include 1 or not include 1 in those intervals, we usually join them together and just say f is concave down everywhere from minus infinity to infinity. That would be the simple way to write the answer here. But you could also say that it's concave down on the interval from minus infinity to 1 with a square bracket at 1, or from 1 with a square bracket up to positive infinity. That would also be a fine way to answer it. And it's never concave up. All right, well, let's add this information to our graph and see if we can come up with a nice graph of our original function f of x. I'm going to move this slide to the right, and if you flip to the next page, it's page 6 of our handout. We're going to add to this graph that I have here and try to fit the concavity into it. Then we'll choose a few extra points to make our graph more accurate. So let's go ahead and see if we can add to this graph by putting in the concavity. We know that the graph is going down till I get to the min and then going up. So don't forget, as we add in the concavity, we can't change that. We can't suddenly make a curve that's going up somewhere else other than what we have. We must generally follow this path in terms of down and up. So try not to lose sight of that overall pattern as you add in the more subtle behavior of the concavity. Well, what did we say here? I'll switch back just for a moment. We said that to the left of 1, our curve is concave down, and it continues to be concave down to the right. Basically, this curve is concave down everywhere. So it is concave down to the left of 1. Let's try to put that part in. Notice the function is going down to the left of x equal 1. And now I want to add in the fact that I want my curve to be scooped downwards. So I don't want it to be scooped upwards and falling. I want it to be falling and scooped downwards. So I have to have a curve that is going down and is scooped downwards. So I don't know exactly where this graph lies, but I want it to be decreasing, but in such a way that it is scooped downwards. When we go to the right of 1, it stays concave down. This is not an inflection point, so I don't want to suddenly flip it to being scooped upwards. I have to follow the green dotted line, so it has to be going up, has to be an increasing function. 2 ways to increase it: can increase scooped upwards or scooped downwards. I want it to be concave down, so I want it to be scooped downwards. So to the right of 1, it increases, but it is still scooped downwards. Well, that is a very rough sketch of my graph. It is better than just the V shape that I had before because it includes the concavity, which is a more subtle behavior of the graph. But how many points have I actually graphed? I've only graphed 1 point, the local mid. So that's probably not enough to know kind of, is this sort of a steep graph that goes up like this? Is it a really wide graph that goes out like this? We don't really know. So we need to put in a few more points. And so here are going to be our extra well-chosen points. And again, what do I mean by well-chosen? I mean, I probably wouldn't plug in something like 100 for x because it's like way off my graph and it's not near anything interesting that's happening. The only interesting point that I found on this particular curve is the local minimum at 1, 0. So since that's at an x value of 1, I might choose a value directly to the left of it, such as 0, and maybe directly to the right of it, such as 2. So I might put those 2 x values in. Now, if I want points on the graph of this function, remember you want to plug these into the original function, which is cube root of x minus 1 quantity squared. So that was our original f of x. Maybe I should put that down here and label it. We're graphing this. F of x equals cube root of x minus 1 squared. So if I want the y-coordinate of a point on the graph of this function, I better plug it into that function. So if I plug 0 in, let's see, when I plug 0 in, I would get -1, but I'm squaring that. When I square -1, I get a +1. When I take the cube root of a +1, I get a +1. So when x equals 0, y equals 1. So this is going to be a point on my graph. I'm going to put the points here in purple. And when I plug in 2, I think I get actually the same output. 2 minus 1 is 1. Square that, I get 1. Take the cube root of that, I get 1. So 2, 1 is another point on this graph. There's a certain symmetry across a vertical line right through the local minimum for this particular graph. So 2, 1. So you can see that my graph really isn't quite right because I've got it a little bit too high. Let's put in, I don't know, another value. What did I put in? I put in 4 and 6, I think. They give us another pair of similar outputs. And when I put 4 into this function, I'll get 4 minus 1 is 3 squared. I get 9, so I get cube root of 9. Cube root of 9, which turns out, for graphing purposes, you can plug it into a calculator. It's approximately 2.1. And I believe if you put in 6, you'll get cube root of 25, which is approximately 2.9. So let me just add those values in here. When I put in 4, I go up to about 2.1. So you can see my graph is just a little too steep in this case. And when I put in 6, you go up to almost 3. So that would be like maybe right here. And I think I also put in the value -2 and -4. When you put in -2, you also get cube root of 9 because of that symmetry I mentioned. So you get an output of about 2.1. And when you put in -4, you also get cube root of 25. So you get about 2.9 as an output. So there's actually a symmetry going on here about the line x equal 1. When I put in -2, I go up to about 2.1. This point's a little bit high, but that's okay. 2.1. And when I put in -4, I go up to about 2.9, almost 3. So let me draw a little bit better graph. So I'm going to draw a graph then that goes through these points. And that gives me a much more accurate graph because I know how quickly this curve climbs. And so I would just cross out this blue graph. That was all just to construct my graph. And if I were doing this for homework or something like that, I would have done the green graph and the blue graph probably in a very light pencil, but you wouldn't be able to see that on the video, so I had to use something darker. But this purple graph is really my final graph. Now there's one other thing that I'll mention that's kind of interesting about this particular problem, although it wasn't asked for specifically in any of the parts we talked about. Let me go back